The last step actually is about compression as well, believe it or not. And if this wasn't coming from Google, I would probably call BS on it, just because it sounded so ridiculous the first time I heard about it. According to a comment in the source code of GWT, sorting the functions by size can actually lead to better compression ratios in transfer. I don't know.
I didn't test it. We didn't test it, which I guess it would be pretty easy to confirm that, but they have enough PhDs from Stanford or Google where I figure they know what they're talking about when it comes to algorithm theory and stuff.
And that's certainly not our specialty.
No.
And the compression works. The obfuscated code from the JSON sample app is almost exactly half the size of the pretty code. And the detailed code is about 7 times as large as the obfuscated code. So you're seeing a significant reduction in traffic. Okay, everyone knows that security through obscurity is bad. But the unspoken truth is that it does help some. When an attacker manages to get source code for a private application, it makes finding vulnerabilities a lot easier. And you know, we've seen that in several cases that have ended up in our forensics lab. We don't have any real proof for it, but our theory is that most Java developers aren't used to their code being accessible to the user. A lot of these guys were probably working on some Struts apps before working on the GWT app. Security through obscurity might be enough to leave some vulnerabilities undiscovered in a pen test or a real attack, but with GWT, a lot of the Java code is going to be pushed to the client in JavaScript form. The method that we used for the compiler example was declared private in Java, but that's not translated into JavaScript. And even if it was, it wouldn't matter because it's all in the browser. One other thing. In the GWT FAQ, Google states that the obfuscation is partially done to protect the intellectual property of the application you develop. I think that's a natural response of that the natural response of anyone actually serious about security is to laugh at a claim like this, but we would actually like to stick up for Google a little bit here.
Yeah, in fairness, I've never heard of somebody developing a top secret algorithm that's the core of their business as part of a web application, and especially not pushing it to the client in JavaScript form. Web frameworks are almost always used for some sort of business application that is fairly traditional, some transactional app, customer service, that type of function. And the value of the intellectual property on an application like that is going to be very closely tied to just however much time the developer spent writing the application. So if someone is intent on stealing that intellectual property, if it was exposed through obfuscated JavaScript, sure, they could go and spend the time to reverse engineer it, to get rid of all the obfuscation. But it would take so much time that, just from an economic point of view, by the time they've reverse engineered it, they would have been better off just writing their own, because it would have cost about the same amount. So in the end, I think that Google's actually right in saying this can protect intellectual property. Well, yeah, go ahead, sorry.
No, to be clear, the tool we're releasing does some reverse engineering, but it's not, it's for pen testing purposes, not for ripping code off of another website or anything like that.
And that's not just the desire for the tool, that we don't want it misused. It's really not what it won't function that way. The intent is to help you attack a site, not to rip it off. It just won't work like that.
RAA services tend to play with the idea of out of sight, out of mind, sort of hiding everything from the user. But just because it's hard to find how to access the services doesn't mean you can't. We've seen a lot of examples of that over the years. In many cases, developers leave service APIs open and ignore proper authentication. So that's obviously a big problem. Additionally, lots of validation for cross-site scripting and SQL injection tends not to be added to the service endpoints. And that's just a case of maybe they're not thinking of it in terms of hitting it with a manual request editor. Lastly, black box testing doesn't exist with RAA. Once the code gets pushed to the browser, it's mine to play with. And while it might appear to be difficult to reverse, Tools not only make it possible to do so, but in many cases make it fairly easy, and as is the case here.
So the code obfuscation is kind of interesting, but GWT's remote procedure call is a much juicier attack target. Rich internet application frameworks are generally characterized by two main things. One is that they have client-side rendering and presentation of the data, as opposed to a traditional application web app where the HTML is going to be generated on the server. And then the second part is that they pretty much all have some sort of function for remote procedure calls. Really, it's like a thick client that's been shoved into a browser and with a database replaced by the web server. In just about every rich internet app that we test in Spider Labs, remote procedure calls are the primary source of vulnerabilities. We see it over and over. It's not really the fault of the framework developers. They almost always will have documentation available saying this is how you should use it, and inevitably developers will ignore that and not include the kind of security that they should be into the remote procedure calls. GWT supports two different types of RPC. One of them is traditional JSON or XML data exchange, which basically you're dealing with AJAX then. The other is a proprietary format of RPC with what's essentially JSON in the response. Most of the developers choose to go with RPC because it's so easy to set up, and so much of it is handled just by the normal framework for GWT. This is a graph from Google's website that sort of describes how the RPC architecture is laid out. Essentially, when the developer is coding RPC, they write the server-side implementation, the receiver, by extending or inheriting the service classes within GWT. The class that they write and all of its methods then become an endpoint that can, when it's compiled by GWT, all of the classes that have to be used in order to support that need to be serializable, but that's not a big problem. Most frameworks that have some sort of persistence or RPC, you have to be able to serialize the data anyway. That's standard. And then finally, the GWT compiler creates a service proxy that will communicate back with the server from the client side. And most of that's automated for the developer. They don't have to worry about the infrastructure to support it. They just define the data that's actually being exchanged and how it's handled. So going to talk a little bit now about the tool, how the deobfuscation works is a lot of it. When I first did a pen test against a GWT app, it was a little intimidating. At first it looked really pretty, which was disappointing because usually the ugly apps are less secure just for whatever reason. But as I started digging into it, realized that there was actually some pretty interesting stuff going on. So this is how the main body of the application looks like when it's sent to the browser. Starts off like pretty normal HTML, just the headers, some JavaScript that's more or less readable. But then you starts off with this huge list of just empty functions. It's kind of weird and apparently redundant, and they keep going for a while. And then you get to some functions that are just return a random name, and that goes for a while, and then you get some slightly more complicated functions. The more you go on, the functions get increasingly complicated, to the point where there's no way that you can tell what they are without quite a bit of work. Now, this one is actually really important. Or actually, maybe it's the next one that's really important. Yeah, this is one that, sorry, here we go. This is related to the RPC, but looking at it, it would be very difficult to tell. There's really not many clues. There's a couple dropped around there if you spend time looking, but there's no way that you can figure out what function it was calling or what type of attacks you could launch against it just by looking at this. So then it continues on with some other garbage, lots of booleans, some strings. This is a little bit more interesting. This is some of the, here we go. This is some of the class names that are in there. So this is somewhat readable, but you have to do a lot of searches within the document in order to figure out how everything relates. So to automate this process, we created Wiglet. It's based on Mozilla Rhino, which is their all Java implementation of the CMonkey JavaScript engine. And it's pretty obvious that it's a port when you're looking through it. It's not written like Java, it's written like C, but in Java. Rhino, though, has a decompiler function that tracks the code while it's parsing it, which is very handy for what I was working on. So basically, I built on top of the decompiler so that a code that would generate a model of the JavaScript that was coming from the server. Tracks things like the global and local symbol declarations, which could either be a function or an object or a class or just a general variable, primitive variable, and then all the references to them. And sorts the references out by type so that basically it's a very flexible model of JavaScript. So want something that you can change and automatically have the changes propagated throughout. If you want to change a function name, for example, if you want to look for all of the references to a member of a certain object. There's 10 basic steps that it goes through to deobfuscate and then pull out some useful information from it as well. The first one is that to extract the JavaScript from HTML, pretty straightforward there. Next, it parsed the JavaScript with Rhino, like I was talking about earlier, resolves the symbol names. The static values are restored. We talked about earlier how one of the steps of the obfuscation was to pull out all the strings and whatnot, and restoring those makes it a lot more readable. The function signatures are processed, and that's one of the biggest things. I'll talk a lot more about that in just a few minutes. JavaScript classes are identified and named. I'll show a little bit about that later too. 7 is to identify the name class getters, which basically has to do with how classes are handled by GWT internally within JavaScript. The callback functions are parsed. Callback is effectively how RPC is handled, where within the browser. Finally, the class fields are resolved where possible to make them a little bit more readable. And then everything is thrown back together, make it look all pretty, a little bit more formatted. So this is, function signatures are a big part of what RegWit does. When I first started approaching it, the problem, my initial thought was really ambitious. It was, well, let's see if we can just directly reverse the obfuscation that Google did. And I started looking more at the obfuscation. The biggest problem with that is that you lose data. The field names are gone, and oftentimes just unrecoverable. So that wasn't going to work. And then my lazy developer side kind of took over, and I thought, well, you know, maybe I can do this in Perl script and just write a Perl script that'll go through with a bunch of regular expressions. And you see sometimes some tools out there, some deobfuscation tools for various languages that do that. The problem is that it is extremely complicated, even though it's theoretically possible, to use regular expressions to parse any kind of language because there's so many exceptions to it. And really the only way to write a good deobfuscation tool is to you build it on top of an existing parser, because writing a JavaScript parser is a huge project by itself, and there's no reason to reinvent the wheel. So once I started doing that, using Rhino, I took a closer look at exactly what was in the JavaScript that was coming down. And really, whenever you're running a program, probably 80% of what is being executed by the CPU wasn't written by the primary developer. It was some library. It was either a system library or some third-party library that they were pulling in. That's true with GWT apps as well. Most of it is either code that's translated from Java, so like a hash map, like I mentioned earlier, or some part of the GWT framework. And every one of those methods is still going to be effectively the same. GWT doesn't use like eval obfuscation like you see on a lot of cheesy websites. It's using, we already talked about how it's set up. So the inherent signature, the flow of every function